So it's a pleasure to welcome Barbara Schapira. Some people of you may have known her from the Olmo mini course together with Keith Burns some happy years ago. There was this Beyond Hyperbolicity conference in Chile. Well, I'm happy to have worked with Barbara on some small project in the happy past. I don't know if this hopefully will come back. I don't know. She's from currently at the Université Rennes, and she's going to talk about amenability of covers of negatively curved manifolds and critical exponents. So please, Barbara.
Okay, thank you very much for this nice invitation. It's quite fun to think that I'm in Rio today. I see a lot of people that I knew, some of you I know from the real life, some others I knew only the names. I see names of people who comes from the world of dynamics and some other more maybe geometers, I don't know. What I will explain is really in between geometry and dynamics. So please don't hesitate to, I don't know technically how it could work, but it would be great if you don't hesitate to ask questions during the talk. I don't know if it is possible. So what I want to explain is a result from a joint work with Rémi Coulon, Rhiannon Dougal and Samuel Papi. And the title is Amenability of Covers and Critical Exponents. And so I will take a lot of time to explain the context and the result, and then hopefully some ideas of the proof. So I will speak about critical exponents. So I will first define what it is. So you consider the hyperbolic space. Depends what is your culture, the typical classical hyperbolic space, if you like, or a Gromov hyperbolic space, if you are familiar with. And you consider a discrete group of isometries. The word is missing. Gamma is a group acting by isometries. I don't, do you see what I write? Okay. So the group acts by isometries on the hyperbolic space, and it's a discrete group. So if you look at your hyperbolic space here, and the points are the points of an orbit of the group, and they form a discrete set. And so inside a ball of radius r, you have finitely many points, and you can count how many points are in a ball of radius r. And it turns out that for many interesting discrete groups, this number grows exponentially. And so you measure the exponential growth rate of the orbit, and it's called the critical exponent. It's a good invariant in many senses. First, as the group is a group of isometries, it does not depend on the choice of the point or whatever stupid choice. It's well defined. And it's also, it's a good invariant in many senses. It coincides with many important quantities in this context. For example, if you are interested in geometric measure theory, you can, I will add a picture. You know that the orbit is discrete, but it will accumulate on the boundary on a set which is called the limit set. I'm sorry, it's hard to do pictures, but and okay, this critical exponent turns out to be the Hausdorff dimension of this limit set, the set of accumulation points of the orbit. More interesting for people who like dynamics, which is my case, it's also the topological entropy in the classical sense of the geodesic flow acting on the quotient manifold. So your group acts on a hyperbolic, X is a hyperbolic space, and you look at the quotient manifold, X mod gamma, and you look at the unit tangent bundle, the set of tangent vectors to the quotient manifold.
Barbara, please, sorry.
Yes.
Could you please repeat the dimension, the definition of the critical exponents, please? Okay, thanks.
So you look at you have a discrete group. Discrete is important, and you look at you count how many points of an orbit are in a ball of radius r. As the group is discrete, you have finitely many points, but this number grows exponentially fast with the when the radius of the ball goes to infinity. And you measure the exponential growth rate of the exponential growth rate of the sides of the orbit. Is it okay?
Yes, thanks a lot.
And so, okay, it's a way to define it which is comfortable for what I will explain today. But what I just explained now is that this quantity, which is defined geometrically here, also coincide with a certain Hausdorff dimension of the accumulation point of the orbit, and also coincides with the entropy of the geodesic flow on the quotient. And now, some obvious remark is that if you consider a subgroup of a discrete group gamma, then an orbit of gamma prime is smaller than an orbit of gamma, of course. And therefore, when you count points of orbits in balls, as I defined, critical exponent, of course, this number for the smaller group is smaller than this number for the larger group. And so the critical exponent of the smaller group is smaller than the critical exponent of the larger group. It's just by definition. And of course, when you are a mathematician and you see an inequality, you ask, when is it an equality? It's a quite natural question. And so you can reformulate what properties of the subgroup gamma prime of gamma will ensure you to have equality in these inequalities. And so, okay, I will first state the theorem and then explain what happened before our result. So what we proved is that, okay, you look at a discrete group gamma acting on the hyperbolic space, take the usual hyperbolic space, if you are not familiar with the one written here, and under some assumption, entropy gap, that I will explain later, under some assumption, we have this result that you have equality if and only if the quotient of gamma or gamma prime is amenable. So maybe there are many words to explain, and I will explain them. But before I explain the words, even if you don't know what is entropy gap, what is amenable, what is whatever, you can just see that we provide a criterion which states that there is equality if and only if some property holds. This result has a long history. It has been proven by Brooks in the 80s by the use of a method of harmonic analysis. Because, okay, I will not enter in this theory, but critical exponents are related to eigenvalues of the Laplacian of the manifold. And he proved an analogous result for eigenvalues of Laplacian in the 80s. There was also in the 80s independent results from a more combinatoric flavor. People considering gamma a free group acting on its Cayley graph, and they obtained this result in this context by purely combinatorial way, counting really orbits in a very special case. I saw that Manuel Stadelbauer is here somewhere. I don't know, but I saw we never met, I guess, but I saw, I see, okay, I see your face. Hi. Maybe we met once, I don't know. Okay, so Manuel Stadelbauer proved for, I don't define right now the assumption, for convex flow compact and some geometrically finite actions of discrete group on the hyperbolic, the classical hyperbolic space HN. So the same statement. Using Manuel Stadelbauer's result, Dougal and Sharp, I saw Richard Sharp, I guess. They showed the same result using coding arguments of the geodesic flow. They extended this result in variable negative curvature. More recently, Coulon, Dalbo, and Sambuzetti obtained similar result for co-compact action on some more general hyperbolic spaces. And okay, you see that you have a theorem which says some property holds if and only if some other property holds. And usually one says that this direction is supposed to be easier. Okay, it's not completely clear, but and this easier direction has been proved in a very general context by Thomas Roblin. But he needed, okay, that's something I will maybe not insist, but he needed that gamma prime be a normal subgroup of gamma. And we don't need this, but I will not insist on this aspect today. Okay, so it's a result which has a long story. And so maybe we had just, okay, we have a version which includes all these, I don't want to detail all these assumptions. What I can say is that our result includes all these and is more general, includes also cases where it was unknown. And more important, I think, is that our result is false as soon as our entropy is not satisfied. That is, we guess that we produced the optimal result. I will explain later what is my assumption of entropy gap. So, okay, what I would like to emphasize is that we have a the most general version that you can hope, including all these results. So now I would like to explain the words of the statement before explaining some ideas. So first I would like to explain what is an amenable group. In fact, I don't want to explain what is amenable. Some of you know the definition, but maybe the easiest way to understand amenability is to understand it from the typical example. Typical examples are Z or ZD, for example. Typical non-amenable groups are free groups. And if for people who prefer dynamics to geometry, if you remember how you proved sometimes in your life that, okay, if you have a map acting on a compact space, then there exists an invariant measure. Okay, you use the fact that you had a Z action, and amenability is the property which makes this argument work. Okay, there are many equivalent definition of amenability, and I will not do a course on amenability, but what we use is this definition, on which I will come back later maybe. You look at the what is called the regular representation of gamma on L2 of gamma mod gamma prime is just a representation defined by, okay, if you have a map phi on L2 in L2 of gamma mod gamma prime, gamma acts on phi by composition. Maybe it's phi of gamma dot or phi of gamma, maybe -1 is missing, I never remember. That's the regular representation. You act on function by composition. And the smaller group is co-amenable in gamma, or the quotient is amenable, it means that this representation almost admits invariant vectors. It means for all epsilon and all finite subset of the group, you can find an element phi of L2 gamma mod gamma prime, which is almost invariant under this finite set. Gamma of phi minus phi is small. That's amenability, but really think that amenable groups are like Z or ZD, and non-amenable groups are like Fn.
Sorry, Barbara.
Yes.
Sorry.
Yes.
Do you have a geometric interpretation of amenability? Like in dynamical systems, how you see the orbit or whatever? Not only from the algebraic point of view. This means what? That you have almost invariant vectors along an orbit, or?
That's a definition of almost invariant. All definitions involve something which is almost invariant. For example, there is a definition saying that there exists a growing family of sets, which is called a Fulner sequence, which are larger and larger, and such that for any fixed gamma and any fixed element, if you, it's difficult to, that's my set, say an, and if I translate it by gamma, I'm sorry that it's difficult to draw a picture. So I have a gamma an, okay, and you look at the symmetric difference between these two sets. So it should be this, okay. Then this should be small compared to an, to the side of an. But it's, if you think to this, what I just said or draw, it's exactly the same as speaking about functions. You can think to your map phi as the indicator function of a certain growing set an, and if you look at the group Z, you will consider, of course, the set an will be the interval minus n. And when you translate them, for example, by 1, you get minus n plus 1, n plus 1, and the symmetric difference has size 2, and 2 over 2n goes to 0 when n goes to infinity. Okay, I really don't want to
Thanks.
I guess that one could spend hours explaining amenability. Really think to these important examples, which are okay, the important examples to have in mind. Okay, that's amenability. And come back to our statement. We say that the smaller group has the same critical exponents in the larger group if and only if the quotient is amenable. But as I said, the critical exponent is, maybe I should, there is a picture mixing. The critical exponent is the entropy of the geodesic flow acting on the hyperbolic space Hn mod gamma. So this space is important, but you have okay, you have two groups, so you have two such quotients, and as gamma prime is smaller than gamma, the quotient by gamma prime is larger than, it's a cover. So you have your manifold Hn mod gamma prime. I'm sorry that I'm not an expert. Okay, Hn mod gamma prime is smaller, so this quotient is larger than Hn mod gamma, and you have a natural projection, and so this is a cover. And so more important than understanding what is an amenable group, it's important to understand the geometric picture, what is an amenable cover. So I draw pictures for that. if you have a compact hyperbolic surface, an easy Z cover of the surface is, for example, this infinite surface. You imagine you have the K graph of Z, and you have a periodic surface of, okay, along Z, you, at each element of Z, you glue a copy of this surface. So it produces Z cover, so an amenable cover. And now I said that the typical non-amenable group is a free group. So it's difficult to draw a free F2 core, but okay, you are certainly familiar with the Cayley graph of the free group with two generators. And so imagine you will glue along this graph hyperbolic surfaces, which are all identical. So you take this kind of piece of puzzle, you say puzzle in English, I don't know. So you take this piece and you will glue it along the Cayley graph of the free group, and it will produce an infinite cover of your piece of hyperbolic surface, and it will be a non-amenable cover. That's a definition, a way to understand amenability or non-amenability more geometrically and less algebraically. And now, if I come back to my statement, there is something that I have to discuss, which is this question of entropy gap. Okay, and okay, if you look at my pictures, you see I draw surfaces which are infinite covers of compact surfaces. So in particular, they are non-compact and have infinite volume. Okay, and when you, there is an interesting concept which is very relevant, in fact, in our study, which is entropy at infinity. So you have a non-compact manifold, and so which is maybe very large, which is okay, that's my manifold, which is from hyperbolic space mod certain group. And when you are interested in dynamics, I said that the critical exponent coincide with the entropy of the geodesic flow in the quotient, but the entropy is the complexity of the dynamics. The complexity of the dynamics can come from the dynamics of the geodesic flow inside a given compact set. Okay, but as the manifold is far from being compact, complexity can rise from infinity. So in fact, you have a compact set, you have orbits which can stay inside the compact set or come back often in your compact set and stay a long time in the compact set. But also you have orbits which can do long excursions outside the compact set. If you are familiar with, for example, Katz's lemma in ergodic theory, you know that excursions outside some compact set can be interesting. And so entropy at infinity is a way to quantify the complexity of the dynamics coming from non-compactness of the manifold. So, and coming from the possibility to have very long excursions. Okay, so there are some ergodic definition of this concept, but what we did is to produce a definition which is really similar to the definition of the critical exponent. We want to understand the elements of the group gamma which correspond to these excursions outside a compact set. And so what we do is to define the following thing. You have your hyperbolic space Hn, and I'm sorry that I'm slow with pictures, and you have a compact set somewhere here, K, and you have its images by elements of the group everywhere, and you want, there are some gamma such that the geodesic segment from O to gamma O correspond to an excursion, for example, here, this green segment maybe correspond to this this excursion outside K on the quotient manifold. And there are other segments which from O to gamma O, which does not correspond to excursion because you go outside of K, you meet K again, go outside, come back. So this is not an excursion. The orange one is not an excursion, the green one is an excursion. And so you count elements, what we call gamma K is the set of gamma encoding the excursions outside a given compact set. And okay, this is a subset of the group gamma. And as it is a subset, you can, if you come back to the definition, let me come back to the definition of the critical exponent, I can measure the growth rate of orbits of this subset. It's not a subgroup, but it's a subset, and I can measure the critical exponent of this subset. And so it produces a number, which is delta gamma K. And when the compact K is larger and larger, one can easily show that this exponent will decrease, and the infimum is a certain number, which is called the entropy at infinity. And it measures really the complexity of the dynamics coming from the infinity. And of course, it's smaller than the critical exponent, and it can be strictly smaller or equal. And we say that there is an entropy gap. We say that there is an entropy gap if this entropy at infinity is strictly smaller than this entropy. Okay. There were different definitions existing in some works about entropy at infinity, but maybe I should emphasize that we produced this geometric definition, which is quite efficient work in the context of geodesic flows, not of other dynamical systems, but for geodesic flows. Okay, and we call, if you have a group gamma acting on a hyperbolic space with an entropy gap, we say that the action is strongly positively recurrent. This terminology comes from, appeared in symbolic dynamics and before, and for example, I don't remember who was the first who used this word, maybe Gurevich or Sarig or Jerome Buzy, also other people. Some funny thing is that exactly the same notion appeared in a completely different community of geometric group theory, and people call that statistically convex co-compactor. And it's exactly the same thing.
Oh, Barbara, does it make
Yes.
sense to ask about the sets K where the infimum is attained, or is this
Just a second, I didn't hear.
the types of sets K, which is the infimum attained? Do the sets K have some property, or is this a silly question?
It's a good question. I have no answer. What we just recently proved is that if you, which we thought it would be an easy proof, and in fact it's not, it's that if you have a compact set K such that you have a strict inequality, then you will have strict inequality here for all reasonable compact sets.
And if K is just a single point?
I know, yes, K should have non-empty interval.
Okay.
But if K is a single point, for example, K is O,
well,
then gamma K will be gamma. And then you will have always equality.
okay.
So it will be relevant for K, which is not too small meaning with non-empty interior.
Thanks.
So the entropy gap at infinite means some kind of regularity of the action, or usually the action is more easy to understand in this case, or?
I don't know what means more easy to understand. I will maybe give some examples with and without entropy gap. Maybe it will answer the question. I don't know. I don't know who asked the question, in fact. Let me see who was speaking.
Daniel is Mania.
Okay. I will give some examples, and if you are, if it does not answer your question, you ask it again in 2 minutes. So, okay, the typical example of manifold without entropy gap is the case of infinite covers. Why? You see, you have an infinite cover. It's an infinite. You have infinitely many copies of the same thing. And so if you take any compact set, as large as you want, it's compact, you will have at least the same things outside. You have at least the same complexity outside K than inside K. It's not a proof, but it's an intuitive idea, okay? So if you have an infinite cover of a given manifold, outside a compact set, you have at least the same complexity than inside the compact set. So you cannot hope that infinity will have lower complexity. So infinite covers of manifolds have no entropy gap. Now, a typical example with entropy gap. Of course, if you have a compact manifold, it's a stupid example, but it has to be said. When you have a compact manifold, if your compact set is large enough, it's the full manifold, and the entropy at infinity will be 0. So you have a critical gap. Convex compact manifolds, from a dynamical point of view, they are exactly as compact manifolds. So they also have an entropy gap. All the dynamics, all the interesting dynamics, the non-wandering set of the geodesic flow is compact, and so it's exactly the same. If you take a compact which is large enough, the critical exponent of the gamma k is 0. Less trivial example, but still well known, is what is called geometrically finite manifolds. Typical example is, okay, I will try a picture. A hyperbolic manifold with what is called a cusp and maybe a funnel, or the picture, and a compact part. For geometrically finite manifolds are manifolds which can be described as the union of a compact set and finitely many ends, non-compact ends. Some of them have finite volume, and some of them have the property that the geodesic which enter these funnels are completely are wandering. If you enter this funnel, you will never come back. And so you have no dynamics here. It's completely dissipative. And so all the dynamics is either in a compact set or in a finite volume cusp. And the philosophy from the point of view of entropy gap, these geometrically finite examples that are manifolds for which you have a compact part here, and you have finitely many ends whose geometry is perfectly understood, and therefore one knows the dynamics. One deduces the knowledge of the dynamics from the knowledge of the geometry of the ends, topology and geometry. And therefore one can, it makes it, okay, since a long time ago, one can work with geometrically finite manifolds. And one should think to manifolds with entropy gap as in the same flavor as geometrically finite manifolds, but from a purely dynamical point of view. One does not know the geometry of the ends. One does not know anything topological or geometrical on these ends, but one just know that their dynamical complexity is strictly smaller than the total complexity. So whatever their geometry is, they do not count in the dynamics. And okay, I tried to draw a typical example. It's not so easy, and my picture is relatively false. But okay, I will come back to imagine this picture. Start from this picture. You have a cover of a compact hyperbolic surface along the graph of a free group, and you will pinch some part. Maybe this curve, and this curve will be shrinked to be very small. This can be done in hyperbolic geometry. And you can produce some example like that. We call them Ancona surfaces because there is a small unpublished paper of Ancona providing an example in this flavor. And so you have a picture like that. You have a piece of surface which has very small, thin ends here, but it's not at infinity. It's something very thin. And outside this compact set, okay, you have some manifolds which have which are copies of the same thing with larger boundary. And the heuristic of the dynamics is that if you take a geodesic here, it will be difficult for the geodesic to go outside this compact set, okay? Because here it's very thin. So it will, most of the time it will stay here. But if maybe, okay, you want to measure the growth of excursion, but if maybe a geodesic goes outside, if a geodesic succeeds to go outside, then you know, it's still very thin, so it will not succeed to come back. Most of the time it will go outside very far. And so if you count excursions means that you start from your compact set, you go outside, and then after some time you come back. It's very difficult both to go outside the compact set and to come back. So if you try to count the growth of your excursions, it's difficult. And so it's an example with entropy. It's just an example, but in fact, there are much more examples that I can maybe not go draw, okay? So don't ask me pictures. But okay. Does it answer the question on entropy gap or manifolds with or without? I don't know. Okay. No more question on. So I will continue. So now I guess that I explained all the words of the statement. Okay. You have, I come back to my statement. You have a discrete group acting on a hyperbolic space, and you have this entropy gap at infinity. And then if you take a smaller subgroup, it has the same exponent as the larger group if and only if the quotient is amenable. That's the statement, and I guess I explained all the words of the title. And this statement has a quite geometric flavor, but what I find fun, okay, that's a question of point of view, but maybe I'm more dynamist than geometer. That is that the proof is completely, almost purely dynamical. So I would like to try to give you a few ideas of, okay, a flavor of the proof. Okay. And I guess that, okay, we are, I should not, maybe it's not the use to say that, but we are quite happy from our proof because really, I think that, okay, all preceding results in this spirit had proofs, but they could not have the most general version because their proof were not general enough in some sense, even if they were very nice or very difficult or both. And okay, so before giving the proof, just a few words on the optimality of the assumption. Our result is false if you consider, I will not enter into details because I will not have time, but if gamma is a discrete group acting on a non-hyperbolic space, the result is false. And if you remove the critical gap assumption, I don't want to do it now, but it's very easy to produce counterexample as soon as you have no critical gap, no entropy gap. So in this sense, our assumptions are optimal. And so maybe, okay, so I have to, okay, I would like to give a few words on the proof, but okay, first I would like to be sure that, okay, is it okay with the statement, or are there some questions on the statement before the proof? Or? Okay, so before the proof, I have to recall something which is called the Patterson-Sullivan construction. And even before that, I have to draw a picture. If you draw the picture of the hyperbolic space, that's the hyperbolic space, Hn. That's topologically it's a ball. And if you take a vector V, that's a vector V, it defines a unique geodesic which has two ends in the boundary, which I will call V minus and V plus. Okay, and the geodesic flow acts on these vectors by translation along the geodesic, and we have a very nice coordinate that is the unit tangent bundle of the hyperbolic space. Okay, it's homeomorphic to the boundary here. I'm sorry, times the boundary times you see, if you have a vector, you can associate to it its two endpoints, but then to really recover V from these endpoints, you need a real parameter to know where is your vector on the geodesic. So you need a real component. And in these coordinates, it turns out that the geodesic flow acts by translation on R. Okay, you see, if you have a vector V, the geodesic flow does not change the endpoints. It just translates V along its geodesic. And therefore, if you want to, okay, I will do now ergodic theory. And so I will have to build invariant measures for the geodesic flow. And if I want to build invariant measures for the geodesic flow, it's as in these coordinates, the geodesic flow acts by translation. If I want an invariant measure, I just have to put the Lebesgue measure here, and then to build interesting measure, say M for the geodesic flow. In these coordinates, it will be some measure, say I don't know, capital M on the boundary, times the boundary, times the Lebesgue measure on M. Okay, these coordinates tell you how to build invariant measures for the geodesic flow. So geodesic flow acts by translation on the real component, and so you know that for building invariant measures, you just have to put Lebesgue measure here, and to complete with a measure on the boundary times the boundary. And the only condition will be remains to have some invariance under the group gamma. And okay, So if you want to interesting measures, you have to build interesting measure on the boundary times the boundary here on the coordinates v minus and v plus. And a way to do that is to construct a measure on the boundary. So what is the Patterson-Sullivan construction? It's a very nice construction of a measure on the boundary. The Patterson-Sullivan construction is a construction, what I say is that it's a construction of a measure on the boundary. I really prefer Blackboard talks. Okay, we have no choice. So how does it work? You first consider what is called the Poincaré series. So you look at all elements of the group and you look at this series, sum over gamma of exponential minus s distance from O to gamma O. And it's like, oh, I don't have to, it's some, I don't have the word in English. It's something that one teach in first years of university. Such series, it's like, in French, it's a série entière, if someone can translate. But anyway, such a series, it's not difficult to see that it has a critical exponent and it diverges below the critical exponent and converges above the critical exponent. And it turns out it's really an easy exercise that this critical exponent coincides with the exponents that I defined before, delta gamma. Okay. And then for s larger than the critical exponent, one builds a measure on the hyperbolic space by this formula. Okay, you consider all the points of your orbit. Oops, no, that's not what I wanted to do. Sorry. You have the point of your orbit. Okay, and you put Dirac masses on all the points of your orbit, but with these weights, which are smaller and smaller when distance to the origin goes. And this, if you divide by the Poincaré series, it gives you a probability measure. Okay, and this probability measure, okay, when the parameter s decreases to the critical exponent, it gives you a measure, and it's easy to show that. Okay, as s goes to the critical exponent, if you take any weak limit of this sequence of measures, it will give you a measure which will, which I call nu, and which will be supported on the boundary. Okay, and in fact, it will be supported on the limit set, what I defined at the beginning of the talk. And this measure, by construction, it's a limit of an orbital measure. And so it has some nice quasi-invariant properties under the group, and which are explicit. So one can write Radon-Nikodym cocycles for the quasi-invariance under the group. And this measure is very useful because when you build the product of this measure by itself, nu times dt on the boundary times r, it produces an invariant measure which on the quotient leads to what is called the Boyle-Margulis measure, and which is the measure of maximal entropy of the jurisdiction, and which in particular is ergodic mixing, etc. It's okay. When you want to do ergodic theory, it's a starting point. It's the best measure that you can dream of. Okay, that's a well-known construction of a classical object. Okay, and okay, our ergodic proof starts from this Patterson-Sullivan construction, and we'll do something quite a little bit crazy, maybe, which is the following. maybe come back to the definition of amenability. You had this representation, regular representation, gamma, consisting just on acting on function by multiplying, by composing them with gamma. Okay, that's the representation, regular representation. And what we want to prove is some properties that this representation almost admits invariant vectors. Okay, so come back to my Patterson construction. I will build what we called a Patterson twisted Patterson Poincaré series. So what do? We consider the sum over gamma of exponential minus s distance of O to gamma O times rho of gamma. So rho of gamma is an operator, a unitary operator. And this sum is a sum of unitary operator with positive coefficients. So if we are lucky, it may be a bounded operator, if it converges in some sense. And precisely, one can define a critical exponent that we call delta rho, which has the property that for s larger than delta rho, this quantity as defines a bounded operator on L2 of gamma mod gamma. It's just a strange object, and yeah, you have a completely formal analogy with the usual Poincaré series. And okay, if S is larger than the critical exponent, you get a bounded operator.
But Barbara, this still depends on rho and the operator you choose?
Yes, yes. It depends, of course. It really contains a lot of information on rho. It encodes the properties of rho. That's a key part of the proof. And the point is that if rho is the regular representation that I defined at the beginning, it's an easy exercise to see that delta rho will be in between delta gamma prime and delta gamma. That's an exercise. It's not it's a few lines to write, but it's not difficult. And in particular, if your assumption of the theorem is that these critical exponents are equal, then of course this is in the middle, so it's equal to all these exponents. And it's the only part of the proof where we use the assumption that delta gamma prime is equal to delta gamma. And we will use it only in the way that if delta gamma prime is equal to delta gamma, then delta rho is equal to delta gamma. That's the only part of the proof where we will use it. Okay, so we have the Poincaré series, and then we have the, okay, we wish to build a Patterson-Sullivan measure, a twisted Patterson-Sullivan measure, so we do it. Then you just have not to be too afraid. We define a measure A rho S by this formula. You look at the weighted, the twisted Poincaré series, and where is my mouse? I'm sorry, I have a technical problem. You look at this formula. You have the twisted series, the twisted Poincaré series, and you put Dirac mass here, and you divide by a normalization constant, which is the norm of the bounded operator, because S is larger. Maybe I should write that. S is larger than delta rho. And so my operator AS is bounded, and so it has a norm, and I can consider this thing. The question is what it is as a mathematical object, and then I'm sorry for the headache. It's a measure defined on the set of, on the boundary. So it takes a Borel set of the boundary, and it associates to it a bounded operator. Okay, you have to be relaxed and not worry about that. It is defined. And the point is that the strategy of the proof will be that when delta rho is equal to delta gamma, we have an entropy gap, No, I'm sorry, I missed a sentence. That is a measure, an orbital measure for S larger than delta rho, and taking weak limits of these quantities, we get a measure A rho on the boundary, which is a measure which associates to Borel sets of the boundary bounded operators on L2 of gamma mod gamma prime. So it's a strange object. You can, we like to think to it as a measure with value, with operator valued measure. A usual measure has values in the set of positive numbers. This measure has values in the set of operators, of bounded operators. And it can be defined, it exists. And then, okay, a key step of the proof is that when the exponents are the same, and when we have an entropy gap, we are able to get a property of absolute continuity of A rho with respect to the classical Patterson-Sullivan measure nu. What does it mean, absolute continuity? It's you have a strange measure with values operators and a classical measure with real values. What means absolute continuity? It means that if you have a Borel set whose new measure is 0, then its A rho measure is 0. And then there is an ergodicity argument. The Patterson-Sullivan measure is ergodic. And then you deduce somehow, as usual, if you have two measures, one is absolutely continuous with respect to the other, and the second one is ergodic, then they are proportional. That's a classical ergodic argument. And then these measures are proportional, but this one is real valued, and this one is operator valued. So the proportionality constant that I call psi is a bounded operator. Somehow it's a multiplicative constant. You just don't have to be afraid about where live your objects, but everything works as in the kind of usual context. And in fact, by construction, the final step is kind of a formal step, because by construction of this measure A rho, which is a limit of such sums, and by construction of nu, which is a limit of analogous sum without representations, these have these two measures satisfy quasi-invariance relation. And so this one is quasi-invariant under the group gamma, this one is quasi-invariant under the group gamma, and so it implies by a sort of formal reasoning that this bounded operator psi, it's an operator which takes values in the set of almost invariant vectors. So this construction produces you. So I recall what was the definition of amenability. Amenability means that you have a sequence of almost invariant vectors. And this construction with multiplicative constant here produce you the almost invariant vectors that you wanted to get. And of course, okay, I guess that I should stop now, but of course there are a lot of details hidden there, but the strategy is really this one. Okay, so I thank you for your attention.
Oh, thank you. Are there any questions?
Yes.
Yes.
Please, Barbara, could you please return to that slide where you were talking about the optima, that the hypotheses were optima?
The hypothesis, I didn't understand. Which?
No, the construction that, okay, you.
This is live.
Yes, this one, the last result, the results found false without a critical gap. And then what is this? I couldn't read this. Okay.
Yes, I wanted, okay, time went too fast, and so I didn't speak about the example.
Okay.
So you want me to produce the counter example without?
No, just to recall, because it was too fast.
No, I didn't. I skipped completely
Okay.
this slide. Do you want me to explain it?
If you could, the last one, please.
Yes. So take a surface S without critical gap. Okay. There are many possibilities, but there exists example without critical gap. For example, sorry, this one, an infinite cover of a compact surface has no critical gap. So you take your favorite surface without critical gap, okay?
Okay.
And then it's a hyperbolic surface. So at some point it will have some geodesic, closed geodesic. It has many closed geodesic, but take two of them. For example, it's difficult to draw a picture. And you can build F2, you cut along two closed curves, and you build a F2 cover of S that I call S prime. You just, it's an easy construction. If you cut your surface along two pieces, two closed geodesics, you can build, you have a building block, you have a surface, a building block like that with four boundary components corresponding to this closed curve that you cut, okay? And then you will glue them along the Cayley graph of free group, and you can build in this way a surface S prime, which is a F2 cover of your surface S, okay? That exists. Okay, that geometry says you that this picture is possible. And then you observe the following point, that the critical exponent, there is, I guess, a problem of notation. This is gamma prime. The critical exponent of gamma is larger than the critical exponent of gamma prime, just because gamma prime is a subgroup, okay? That's easy. Then the critical exponent of gamma prime is larger than its critical exponent at infinity, just by definition. It's also by, it's not hat, it's prime. It's a mistake, okay? Just because the entropy at infinity, by definition, is smaller than the entropy. But then the key point is that by construction, you know, my surface, maybe I will take the same color, yes. Here I have my surface S, which has entropy at infinity coming from the ends of my surface here. My surface S is non-compact, but here in my construction, S, I have the same ends here. And so the complexity which arise from the infinity in S arise still here in this construction, and will also which will remain in S prime. And so in this construction, it turns out that the entropy at infinity of gamma prime is equal to the exponent at infinity of gamma, because the ends of S and S prime, S primes contains the ends of S. So S prime is more non-compact than S, but it is at least as non-compact as S. So the entropy at infinity of S prime, in fact, is larger than, maybe I should write that it's larger than the entropy at infinity of S. But then, okay, this is always true. And this is always true. It has nothing to do with the entropy gap. Okay, and the key point that here we have no entropy gap is that here I have an equality. And then all these inequalities are equality. Okay. But however, okay, you see, therefore it implies that delta gamma prime is equal to delta gamma, but however, S prime is a F2 cover of S. So it contradicts our theorem. It does not contradict because it has no critical gap, but it does not satisfy the conclusion of the theorem. And it's really because there is no critical gap.
Okay.
Are there any other questions?
Thanks. Thanks.
Can I ask a small question?
Sure.
Yes.
Maybe it's a little marginal, but when you mentioned this kind of manifolds that where all the dynamics are contained in a way in a compact region, you mentioned that on the ends you need to you mentioned the singularities are cost points.
Yes.
My question is yes, that's right. If the dimension of the manifold is large enough, are you certain that the singularity will be a cast point, or can there appear other kinds of singularities?
No, in fact, okay, there are. It was a slightly too fast, probably. There are two kinds of manifolds. This convex compact one are those where a typical picture. I draw pictures in dimension 2 because I don't know how to draw pictures in higher dimension, but it's really the same. Okay, it's a typical picture is, for example, a punctured torus where you have a hole like that. Here you have a compact part. Here you have a non-compact part. But the point is that if you have a geodesic which enters here, it will never come back.
Yes,
and
yes, I understood the explanation. My question is, because you mentioned the singularities, you talked about them as costs. And
I'm not sure to understand what you call singularities, but it happens. The example which is just beyond this one is an example where, okay, in this example, convex compact, it turns out that the non-wandering set of the geodesic flow is a set which is transversally a contour, which is the set of geodesic which stays in this part, okay? And it turns out that it is compact. So these convex compact manifolds are exactly the manifolds such that the non-wandering set of the geodesic flow is compact. And then the slightly more general example is the geometrically finite case where you have cusps. And okay, these cusps, there are geometric ways to characterize them. In the dimension 2, it's easier because it's really a kind of hyperbolic cylinder with finite volume.
Yes.
But in higher dimension, you can define it as the quotient of the hyperbolic space by a parabolic group. And it's not always a finite volume because the parabolic group is maybe not of maximal rank, but it's still true that it's in some sense on the quotient manifolds it gives you a small end. It's seen in some sense, and okay. So and the point is that the geometry of such ends, okay, yes. It's maybe, of course, it's simpler in dimension 2, but still the idea is always the same. It's that if you go inside, you will turn I'm sorry that I'm not able to do a nice picture, but you turn around and going up, and at the end you turn around going down, and then you come back. And the time that you spend inside corresponds to the number of turns, and okay, the dynamics is easy to understand. And complexity, explicit computations say you that the complexity of this cusp is smaller than the total complexity in percent curvature. If some of the audience like variable negative curvature is not true.
Sorry, may I ask a question?
Yes.
Sure, sure.
It seems that these small, thin things that you take is like a fake end. More or less.
Fake.
Huh? Fake in the sense that, okay, it's not in the infinity. You have some obstruction here.
No. It's really infinite. It's just that my picture is it's really non-compact. It's really infinite. It's really unbounded. It's really that I'm unable to draw a correct picture. It's really an infinite. Okay, if you are familiar with the upper half plane for the definition of hyperbolic space, it's the quotient of such an area in the upper half plane by an horizontal translation. Okay.
Okay.
So it's this region. Okay. If you draw it on the quotient, it will give you something like that.
Okay.
That's okay. In dimension 2. Of course, in a higher dimension, it's a little bit more complicated. So it's really infinite, but it has finite volume, and one understands perfectly well the dynamics inside.
Okay, thanks.
Barbara?
There's a question
Yes?
by Das. If there's any connection, he doesn't have a good internet connection, so he's just typed in the chat. You can see, is there any connection of your exponent with the convex core entropy of Falk Matsuzaki that is worth remarking?
It's a shame that I read Falk's articles a long time ago on convex core entropy, and I don't really remember, but I think what I remember from it is that there is a kind of geometric definition of entropy, which is called the volume entropy. And if you have a compact manifold with non-positive curvature, this volume entropy coincides with the topological entropy. Maybe if I come back to the critical exponent, the volume entropy is the quantity, maybe I can write, is the limb soup of 1 over r log of the volume of a ball of radius r. And there is an old result of Manning, which says that if maybe we'll write here, if the manifold X mod gamma is compact with non-positive curvature, then the volume entropy is equal to delta gamma, the critical exponent. And I'm not sure to remember exactly, but what I remember from Falk entropy is that his maybe convex core entropy is a kind of generalization. Okay, if you have a manifold which is for even a convex compact manifold, I gave this example of a punctured torus. The interesting set for the dynamics is a set which is transversally a counter set. So if you look at in the universal cover, the volume of the lift of this set will be 0. And what I remember from his work is a kind of generalization of the geometric notion of volume entropy. For non-compact manifold. Defining a kind of volume on the convex core. The convex core being what I call the non-wandering set of the geodesic flow. I don't know if it answers the question, but I think that's a good answer. So the conclusion is that it has nothing to do with entropy at infinity, I guess.
You see the chat for he answered for the convex core entropy, you intersect the ball with the epsilon convex hull of the limit set in the definition you reminded above.
Yes, so I don't see the chat, I'm sorry.
There is, besides the share screen, there's the chat and you can open the chat.
Don't worry about this, I think that is.
I can send you afterwards his chat. Well, he has a second question. I don't know if this is answering.
So, yes, what he says is exactly what I remember. It's a generalization of the notion of volume entropy.
Okay, good. Yeah, he has a second question about didn't mention whether the group is of convergence or divergence type when you define the Patterson-Sullivan measure. And he asks, I assume that your twisted operator valued measure is well defined in both cases. Is there anything interesting you wish to add about this?
Okay, I'm not sure to have understood completely. The point is that, okay, convergence of divergence is a good question, but under the assumption of entropy gap, it's an independent result that we proved in another paper, but entropy gap implies that the group is of divergence type.
Okay.
It implies that when Margulis measure is finite, it implies that the geodesic flow has a finite measure of maximal entropy. And so I didn't understand the second part of the question. But
no, I think this answers, because he was wondering if it's of convergence and divergence type, and then the consequences for this operator valued measure. But I think if it is of convergence type, so then for this makes sense.
It's also always of divergence type.
Okay, yes, no, this answers this question. Any other questions?
Yes. Do you have any control on these invariant vectors? Does the proof provide, so you have this proof and you get these constants somehow from the ergodicity argument? And my question would be if you have any control of the operators you get out. It is step 5 in the proof.
Yes. I know. That's a good question. In fact, this construction provides okay, this slide does not bring anything, but you get yes, you get invariant vectors, and you get an operator whose values are in the set of almost invariant vectors, and so we are happy. But there are many things which are unexplored in this construction. I mean, you see, in this construction, one funny thing is that, in fact, we don't use that it is a regular representation. You see, the only place where we use it is really at the beginning, when we use it to show that the only place where it is useful is here, to show that the critical exponent delta rho is in between the two exponents. And then, of course, if your assumption of the theorem is that the two critical exponents coincide, delta rho is in the middle and coincide with the two others. But you can do the construction for an abstract representation rho and work with the assumption that delta rho is equal to delta gamma. You don't know, you are in an abstract world. Anyway, this construction is completely, has something a little bit crazy. And then, okay, and you get almost invariant vectors. But we at the moment, we don't understand much more. We understand that this construction is quite magic, but we would be happy to. What we guess is that this construction should give more results in the future. But at the moment,
But there should be some relation to Fellner sets somehow. So maybe it's possible to control them.
You see, of course, it's a relation with Fellner set, because if you produce an almost invariant vector, it's the same as a sequence of Fellner set, but Fellner sequence. But you see, there is an ergodicity argument saying that I don't know why is it so. This ergodicity argument says you have a measure which is absolutely continuous to another, and with ergodicity, then they are proportional, but the proportionality constant, you just know that it exists, you see, and you also just know that as your two measures are non-zero, this constant will be non-trivial, and so you produce really a non-trivial operator, and then you really get at the end some almost invariant vector. Okay. But it's purely abstract and magic. So for the moment, I would be happy to have other applications of this construction, but we are far to understand really what we did.
Okay, thank you, thank you.
Yeah, are there any other questions? Then let's thank Barbara again for this very nice talk. Okay.
Você quer dizer alguma coisa?